Hello everyone. In this video, we will be discussing seismic signal analysis. This project was done by Karan Jagtap, Soham Jadhav, and me, Vinay Gupta, under the guidance of Professor Najib Ghatte. We hope you find it interesting and informative. So let's get started. To the purpose of project. The goal is to explore and refine methods in seismic signal processing, which is crucial for accurately detecting and interpreting seismic events like earthquakes. The precise analysis can differentiate between true seismic events and background noise, potentially identifying early signs of earthquakes or significant geological changes. The project can be divided into two phases, progressing from fundamental techniques to advanced processing methods. Phase 1 focuses on building foundational knowledge and implementing basic filtering and signal transformations, whereas the Phase 2 advances to sophisticated signal analysis techniques, enhancing real world applicability. So let us move to the introduction to seismic processing, signal acquisition. Seismometers are our primary tools for gathering seismic data. They continuously record ground vibrations, providing a detailed stream of information that reflects the seismic activity in a particular area. This real-time data is starting point for any seismic analysis. Filtering. Seismic signals are often cluttered with noise that can obscure meaningful information. Filtering helps us eliminate irrelevant frequencies, allowing us to focus on frequencies that truly represent seismic events. This is crucial for making the signal clearer and more reliable for analysis. Event detection. In this step, we pinpoint significant fluctuations that may indicate seismic events. By setting thresholds and using statistical methods, we can distinguish between normal ground vibrations and actual seismic events, increasing the accuracy of our detection process. System response. Modeling the system's response allows us to simulate how seismic waves interact with geological formations. This gives us insights into how seismic energy propagates through the earth, which is essential for understanding the signal's impact and behavior in real world contexts.
Let's dive further into the topic and understand how a signal, which is represented in a time domain, is converted into a frequency spectrum. Let's take a brute force approach. If you want to know how much of a particular sine wave is in a signal, just multiply the signal by the sine wave at each point and then add up the area under the curve. As a simple example, say our signal is just a sine wave with a certain frequency that we pretend we don't know, and we're trying to figure out which sine waves add to make it up. Well, if you multiply the signal by a sine wave of an arbitrary frequency, the two waves are uncorrelated. You are just as likely to find places with the same sign, both positive or both negative, as where they have opposite signs. And therefore, when you multiply them together, the area above the x-axis is equal to the area below the x-axis. So these areas add up to zero, which means that frequency of sine wave is not part of your signal. And this will be true for almost all frequencies. You could try assuming for a long enough time frame. The only exception is the frequency of the sine wave exactly matches that of the signal. Now these waves are correlated, so their product is always positive and so is the area under the curve. That indicates that this sine wave is a part of a signal. And this trick works even if the signal is composed of a bunch of different frequencies. If the sine wave frequency is one of the components of the signal, it will correlate with the signal, producing a non-zero area. And the size of this area tells you the frequency sine wave in the signal. Repeat these processes for all the frequencies of the sine waves, and you get the frequency spectrum, essentially which frequencies are present.
Let's break down the code step by step, explaining each section in a way such that it is easy to understand. Firstly, we generate or load the seismic signal. Here we have generated a seismic signal using this random function. Firstly, the sampling frequency. Sampling frequency is the rate at which we sample the signal. Here it is set to 100 Hz. This ensures that we get a high resolution to capture the seismic signal. Nextly, we have the time vector. The time vector spanning from 0 to 10 seconds with interval of 1 upon fs. Thirdly, we have the randomly generated seismic signal. Now, we will perform Fourier transform on the seismic signal. So, firstly, this is the length of the signal. Length of the signal stores the number of samples in which the seismic signal has to be stored. This is to compute the FFT of the signal. FFT stands for fast Fourier transform. It converts time domain signal to frequency domain, giving us the signal's frequency component. The factor P2 gives us two-sided spectrum. This is to create a two-sided spectrum containing both positive and negative frequency. The variable P1 gives a single-sided spectrum. Here we take two-sided spectrum since real-world signals are typically analyzed in one direction of frequency, that is only in positive direction. And then we have this frequency vector. Frequency vector is the that vector which aligns the single-sided spectrum, giving us corresponding frequency. Then we will design a low pass filter. The low pass filter, in low pass filter, we have set the cutoff frequency to 10 Hz. Also, we have used a Butterworth low pass filter. Butterworth filter is a type of low pass filter that is smooth in its frequency response and effective at eliminating the high frequencies. Here, the filtered order, meaning it has a sharper cutoff. So, it will have the higher order, so so it will suppress more frequency. Applying the filter. Applying the filter is the major step in the process. The filter applied is the design filter to seismic signal, removing frequency above 10 Hz. This creates a smooth signal, mainly retaining the components below 10 Hz. Then we have the event detection. Event detection. In this, we set a threshold at 80% of max frequency, max amplitude. Then we also find the samples exceeding the threshold frequency. Then we have the system responding model using a transfer function. This is a transfer function, where S is the transfer variable and H is the system response. Then we have to apply the system response to the filter signal. Here we have done the same thing. It simulates the response of the system H to filtered signal over time vector T. This provides response output of the system when subjected to filtered signal. Then we have the final plotting of signals in sequence. Here we plot the signals with help of graphs with the help of inbuilt functions like plot and subplot. Now let us look at the graph. The first one which you can see in the red color shows us the unprocessed seismic data as a as depicting amplitude variations over 10 seconds. Frequency spectrum of the seismic signal. This graph basically displays the frequency content of the signal, showing peak at specific points like you can see here, and indicates dominant components. Then we have the filtered seismic signal. These signals here we show the filtered version of the seismic signal of this graph basically. Also, with the specific events like significant signal peaks, you can see they are marked with red circles. Also, lastly, we have the system response of the seismic signal. Here we illustrate how the system responds to the seismic signal, possibly indicating the oscillatory behavior of the time.
Now let's take a look at Project 2, which is an advanced version of Project 1. In Project 1, we have designed a simple low-pass filter to remove frequencies above 10 Hz, preserving only lower frequency components of the signal. This approach is effective for isolating low-frequency seismic events, but lacks precision for filtering out specific frequency bands. Here, we have implemented a more advanced band-pass filter, ranging from 1 to 10 Hz, to isolate a relevant frequency range and add a notch filter to remove specific noise frequency. Here we can see we have implemented a notch filter via MATLAB inbuilt function. The notch filter further refines the signal by eliminating known noise frequencies, resulting in a cleaner analysis, which provides targeted frequency isolation, allowing for a clearer signal with minimal noise, which improves the accuracy of event detection and overall analysis. In Project 1, we have utilized a fixed threshold set at 80% of the maximum amplitude to detect the seismic events. This approach is straightforward, but may miss events in noisy signals or over-detect in low amplitude noise. In Project 2, we have used a dynamic threshold based on the statistical measures, which is 2 times of the standard deviation. Here we can see that we have implemented the advanced threshold detection for statistical measures. This dynamic threshold in Project 2 is more adaptable, enhancing event detection accuracy by accounting for the noise profile in the signal. In Project 1, we have used only the Fourier transform to analyze frequency components. While effective for overall frequency insight, it lacks time localization, which limits its ability to analyze the transient events, which is short-lived seismic signals. In Project 2, we have included a wavelet transform for time frequency analysis, enabling better localization for transient events over time. This is particularly useful in seismic analysis where events may have short durations and specific frequency range. Now let's have a look at the wavelet transform of a filtered seismic signal. This continuous wavelet transform provides us an in-depth analysis and decomposes the signal into different frequency components over time, allowing us to observe how the signal's frequency content evolves. Here's a breakdown. On the y-axis, we have frequency ranging from 10 to approx of 15 Hz. In seismic signals, different frequency ranges can correspond to different types of seismic activity or noise sources. On the x-axis, we have the time scale. This corresponds to the same time period as the original signal plot, which can be witnessed here of our raw seismic signal. The amplitude or the color scale. The color intensity represents the amplitude of the signal at each frequency and time. Higher amplitudes are shown in yellow colors, while lower amplitudes are in blue. These high energy regions highlight significant events or peaks in the signal, potentially indicating seismic events, which we have shown in the filtered seismic signal, and the red circle shows us our detected events. To correlate with the detected events, the filtered seismic signal is shown with red circles, which is these ones, marking the detected events. These events correspond to the peaks in signal amplitude that exceed a threshold based on the twice of standard deviations of the filtered signal. To compare this with this spectrograph, the detected events in the time domain plot tend to align with the areas in the spectrogram that show high energy, which can be witnessed by the color yellow or the dark ochre. These high amplitude regions in the spectrogram suggest that the detected events have a stronger presence at lower frequencies, which is typical of certain types of seismic activity. And here we can see this is a raw seismic signal which was detected by us. And this is the frequency spectrum which is converted via the Fourier transform. And as we filter it further, the red circle marks us the event detected, which is of the higher amplitude, indicating the earthquake occurred at this frequency. This is the system response of a filtered seismic signal, which tells us how the seismometer or the model which is used to detect the earthquake events may produce the graph.
So let us go through the key concepts used in our project. Fourier transform. The Fourier transform converts a time domain signal into its frequency domain representation, letting us see the individual frequency components. This helps identify different seismic events by analyzing their frequencies. Second, Butterworth bandpass filter. Next, we use a fourth order Butterworth bandpass filter with a range of 1 to 10 Hz. This filter isolates frequencies relevant to seismic activity, removing unwanted noise for a clearer signal. Third, dynamic threshold for event detection. Our dynamic threshold adapts to the signal's variations, marking unusually high amplitudes as seismic events. This helps avoid false positives caused by random noise. Fourth, Laplace transform. Finally, the Laplace transform simulates the system's response to seismic events over time, showing how a real world system would react to detected signals. Together, these tools filter, analyze, and interpret seismic data, providing a clearer view of seismic activity. In moving to the conclusion, in summary, our seismic signal analysis applies advanced techniques to clean, analyze, and interpret seismic data. Filters like bandpass, low pass, and notch isolate essential frequencies, while dynamic threshold ensuring reliable event detection by adapting to noise. The Fourier transform reveals frequency details, and wavelet transform enhance time frequency localization for transient events. Finally, system response modeled with transfer functions show how filtered signals interact within dynamic systems. Thank you for watching our video on seismic analysis. We hope you found it insightful and learned something new. If you have any questions or feedback, feel free to share them in the comments. See you in the next one. Thank you.